Binary search is a search algorithm. It takes as input an array that we will call a haystack and a value that we will call a needle. Unlike in other search algorithms, the haystack must be sorted in, say, increasing order of values. Binary search determines if the needle is in the haystack or not. Furthermore, if the needle does occur in the haystack, it also returns the position in the array at which it can be found. Binary search is a little bit like the Bluetooth tags that you can attach to your keys to quickly find them, in that it is very fast, but you must first remember to have your array sorted, just like you would need to tag your keys before actually loosing them. The trick in binary search is to shorten the search space at each step by excluding large parts of the array where the needle cannot possibly be found. At each step, we will use two indices, L and R, such that everything to the left of L is smaller than the needle and everything to the right of R is larger than the needle. Therefore, the needle can only be in the segment between L and R, if it occurs at all in the haystack. For this reason, we call the segment between L and R the segment of interest. Initially, the segment of interest consists of the entire array. Binary search shrinks the segment of interest at each step by roughly a half of its size. Therefore, we either find the position of the needle after not too many steps, or the segment of interest reduces to the empty segment, in which case the needle does not occur in the haystack. Let us take a deeper look at how the segment of interest is reduced. At each step, we analyze the value of the element that sits right in the middle of the segment of interest, which we mark in blue. For haystacks with an even number of elements, there is no element right in the middle. In this case, we choose to mark in blue one of the two centermost elements. It does not matter much which one. Once the blue element is chosen, there are three cases to consider. In the first case, we get lucky and the needle matches exactly the value of the blue element, in which case we are done, we have found the needle and we return its position. In the second case, the blue element is smaller than the needle. Because our array is sorted in increasing order of values, all elements before the blue one are even smaller and therefore cannot contain the needle. This means that we can reduce the segment of interest by moving L just after the blue element. In the third case, the blue element is larger than the needle. All elements after the blue one are even larger and cannot contain the needle. Therefore, we reduce the segment of interest by moving R just before the blue element. At each step, the length of the segment of interest is roughly cut in half. We must either get lucky at some point and hit the needle, or we end up with an empty segment of interest, and in this case we know that the needle does not occur in the haystack. Here is how binary search works on our running example. We start with L pointing to the leftmost element, and R pointing to the rightmost element in the array. Let's forget for a second about the actual contents of the haystack. We compare the element in the middle of the segment of interest, which is 5, against the needle. It is smaller than the needle, and therefore we restrict the segment of interest to the half on the right-hand side. We compare the element in the middle of the new segment of interest, which is 8, against the needle. It is larger, and therefore we restrict the segment of interest to the half on the left-hand side. We now compare the single element that remains in the segment of interest against the needle. They match, and therefore we have found the needle and its position. Note that we have only accessed 3 out of 7 elements in the input array, and this hints at the reason why binary search is so fast. Binary search will, in general, only access a number of elements logarithmic in the size of the haystack, and therefore its complexity is theta of log n. Let's also try another example in which the needle is not in the haystack. We start with L pointing to the leftmost element, and R pointing to the rightmost element in the array. Let's hide the contents of the haystack for now. As the number of elements in the segment of interest is even, there is no element directly in the middle. We choose to compare the needle against the element situated just to the left of the middle, which is 4. It is smaller than the needle, and therefore we restrict the segment of interest to the half on the right-hand side. We compare the needle against the element in the middle of the new segment of interest, which is 6. This element is again smaller than the needle, and therefore we restrict the segment of interest to the half on the right-hand side. We now compare the needle against the single element remaining in the segment of interest. It is larger than the needle, and therefore we restrict the segment of interest to the left-hand side. Our segment of interest is now empty, and the needle is therefore not in the haystack. Let us implement binary search in the C language. We start with a function binary search. It takes as input an array called A containing the haystack sorted in increasing order of values, an integer n representing the size of the haystack, an integer needle representing the value we are looking for, and it returns a position at which the needle occurs in the haystack, or the special value -1 if the needle is not in the haystack. We start by initializing the two indices L and R as discussed above by the first and the last element in the array. We now loop for as long as the segment of interest contains at least an element, and therefore there is a chance of finding the needle. needle. We store in the variable m the middle of the segment L to R, rounded down to the nearest integer. We check if the needle is exactly at position m, and if it is, we return this position. No such luck in our example. In the case where the element at position m in the haystack is smaller than the needle, there is no chance to find the needle to the left of m, as those elements are even smaller, and therefore we update L to m+1. In the last case, where the element at position m in the haystack is larger than the needle, there is no chance to find the needle to the right of m, as those elements are even larger, and therefore we update the value of R to m-1. Finally, for haystacks where the needle does not occur, the segment of interest becomes empty at some point and we exit the while loop. In this case we return -1. Subscribe to the Truly Understanding Algorithms YouTube channel by using the button in the middle of the screen to stay up to date with our videos that help you better understand interesting algorithms and data structures. Give us a thumbs up and leave a comment with topics that you would like us to cover in the future. Also visit trulyunderstandingalgorithms.com to read a textual version of this tutorial.